In the last few years, the pace of developments in the broad area of quantum technologies has been quite fast. So much so that we started seeing at least some products out in the market that are based on quantum technologies. There are products that are based on quantum cryptography, quantum sensors that are now available in some sense as off-the-shelf products. But the crown jewel, so to speak, of the entire quantum technologies is really building a general purpose quantum computer. A general purpose computer that would be able to take any problem, solve it more efficiently than a classical computer. Really, we are far away from such a goal. And in fact, it is not even clear that we'll ever get to that point at all. It might be that we'll have to work with quantum computers, which can solve certain classes of niche problems, but we'll probably never have a quantum computer that would do pretty much anything just like our desktops are able to do today. Nevertheless, we are in a phase where there are many quantum computers, at least a few quantum computers available as a cloud service. And to use them, there are also many algorithms which are available. For instance, at least for the last 30 years, we know of a quantum algorithm for prime factorization, which gives an exponential speed up over classical algorithms. And there are algorithms for searching an unstructured database, which even if it does not give an exponential speed up, does give a quadratic speed up. And now we have a host of other algorithms, for instance, for pattern matching, for combinatorial optimization. Many of them do not give exponential speed up, but do give some kind of polynomial speed up over classical computers. Which means that we can actually take advantage of both these developments. We have a large class of algorithms which are available, and we also have some quantum computers which are available as a cloud service. We can actually take these algorithms and maybe try and see if we can solve some of the problems that would arise in real applications. And it so happens that now we are in a phase where we can actually solve some of these, at least attempt to solve some of the more realistic problems that arise in industry. In many of these cases, ultimately you can reduce them to solving one or the other of a standard mathematical problem. For instance, it could be trying to solve the linear system, a large eigenvalue problem, or solving ordinary differential equation, or could be an optimization problem, or some kind of machine learning problem. So there are quantum algorithms for pretty much most of these things. So along with quantum algorithms, in recent times, there has been quite a bit of work on quantum machine learning as well. So we should be able to translate at least some of these algorithms and use the quantum hardware that's available to see if we are able to take advantage of these things. And in the context of India, there are many interesting problems which could be addressed, and that could range from things like drug discovery or logistics problems, and all kinds of optimization problems, new materials, machine learning, and security or defense related problems. Finally, maybe I would like to point out that it might so happen that we might not ever be able to build a general purpose quantum computer that would be as dynamic as our current desktops. But nevertheless, in about a decade from now, we will certainly have powerful quantum computers which will be able to address many niche problems, or which would be good enough for certain classes of problems. That would be a good starting point to take this area further ahead. Thank you.